We'll get into the ionosphere. Now, this picture up here is certainly not the ionosphere. Anybody know what this particular drink is called? Anybody ever have a Pousse Café? Okay, a Pousse Café. Now, what we are going to be talking about is different layers of the ionosphere, and those layers are defined by density. There's heavier parts of the ionosphere, there's lighter parts of the ionosphere. We'll be talking about those layers. For fun, I like to throw this in here. These are different liqueurs in the glasses, and depending on the liqueur, some of it is very heavy, some of it is very light, and a good bartender knows how to pour these things very carefully, because like this one here, it's starting to mix, I think. But the heavier stuff, the grenadine, I think, is down at the bottom. You get the, what do you call this? I can't remember. I'm not a drinker of this stuff. Curacao, I think, is the word.
Curacao.
Yeah. Yes.
So the C has the little C.
Yeah, that little mark down there.
Yeah, that's what pronounces that as an S.
As an S.
Yeah, my maiden name's Portuguese, so there's a C, but there's the little C that's attached to it, and it's pronounced with an S.
Oh, gotcha. All right.
I forget what the little C's called though. Whatever.
A little squiggly one.
Yeah, it's a lot in the French language too.
Okay. Well, there you go. You got the French and the Portuguese at work here with Pousse Cafés. All right, the ionosphere. This is a region from 30 miles to 260 miles above the surface of the Earth. The atmosphere is pretty thin up there, and it's thin enough that atoms can be atomized by solar ultraviolet radiation. So we don't worry so much about it unless it's a good summer day. Well, it can be too on a sunny winter day as well. We don't worry that much about ultraviolet, except some of us who have very dainty skin. We want to put sunscreen on no matter what. But it really affects the ionosphere up above us. Ions are electrically conductive, and so we use this to our advantage, or to the advantage of transmitting radio waves. Anybody see the launch yesterday, whether live or recorded? Wasn't that awesome? Now they, I know the channels I was watching, both of them were ironically being hosted from other countries, not the United States. So all of their descriptions of speed and altitude were in meters. And I think they got up to about 100 kilometers anyway, 150 kilometers. I have no idea. I think it's 2.2 kilometers to the mile, so maybe 70 miles up, somewhere up there. So they were just getting into the ionosphere with that rocket. Okay, so here are the layers. And because of the varying density of the ionosphere, layers are formed with different amounts of ionization. So down here in the stratosphere, 6 to 3 miles up, it's pretty dense down here. Below the stratosphere, it's troposphere where we are. This is where most of your weather takes place. Stratosphere is 6 to 30 miles up there. And above the stratosphere, now we're getting into the ionosphere. The D layer, the E layer, the F1 and F2 layers. And F1, F2, they've broken it down that way because during the day, you will have two distinct layers there. But at nighttime, those two layers combine together. So instead of calling it the F and the G, they decided to call it both of them F layers, F1 and F2, because at nighttime, the F layer is just one layer. Ionization varies with solar illumination, hour to hour, and intensity of solar radiation. So what does that solar illumination, we're talking the sun. So things can get very active when during daylight hours when the sun is up there shining through our ionosphere. Higher ionization refracts or bends radio waves more strongly. So there are certain, again, we're talking mostly HF bands, and that's from the amateur radio point of view. Just talking about HF in general, it applies across the spectrum there. The ionosphere. Now, I disagree with this title. The ionosphere is an RF mirror. Well, we had just talked about the difference between reflection and refraction. Mirror implies reflection, but what's really happening here is refraction. So refraction depends on frequency and the angle of incidence. That's the angle at which your radio wave is taking off on your antenna. So as we discussed earlier, here's one that's just shooting off straight into space. But that same transmission, there's something here, the angle of incidence is going at a different angle. And because of that angle, it actually reflects up here, or refracts up here in the ionosphere and comes back down to Earth on the other side here, a single hop. Same thing could be happening from this station here, or it could be reflecting off the Earth and making another hop. This angle also goes off into space. So too high a frequency or angle, and the waves are lost to space. More refraction of HF signals is done in the ionosphere, in the F layer. And that's, yeah, so that's pretty high. That was, you'll recall, the highest one. And we're going to talk about this, what we call the maximum usable frequency and the minimal usable frequency coming up in just a minute. Ionosphere can refract radio waves back to Earth, acts like a reflection. Okay. Most refraction of amateur frequencies, particularly HF frequencies, occur in the F layer. So remember that. And I don't think it mentions it here. You'll get it in the general. But that first layer, closest to the, just above the troposphere, or the stratosphere rather, the D layer. The D layer during the day is very active. D layer during the day absorbs radio frequencies. So suddenly, sometimes you're hearing things real clear at nighttime. And then during the daytime, you don't hear anything so much at all. And this is all because of the D layer is absorbing rather than refracting anything. Best conditions on 10 meters happens during the high sunspot activity between dawn and shortly after sunset. So on 10 meters, the D layer doesn't affect 10 meters as much as it does when you get down into the much lower frequencies. In fact, one or two of the bands, 80 meters and 160 meters, that's 3 megahertz down to 1.6 megahertz, that's just above the AM band, broadcast band, really gets hit hard. And in fact, in the summertime, those two bands are what we call closed. You can't propagate anything on those frequencies, especially during the day. And again, here's, I think this is probably the third different illustration we've had of things being refracted by the ionosphere. But what this one puts a little more detail into what a skip zone is, where there's no reception. That was kind of like me with Kenzie down there. I am barely into the skip zone. The ground waves just barely making it. But all of her signals are going over my head, being picked up by up and down the coast, New York down to Florida. Good reception. And so it's like here's New York, here's Florida in her area of reception for her transmitter. But I was right over here in this corner between where the ground wave reception ends and the skip zone picks up. We're going to talk about antenna lobes in the next section. So angle of incident is kind of what this, okay, who's the Greek speaker? Is this a theta? Rho? No? I don't know either. Anyway, this is the angle of incident. As that angle of incident varies, your signal path also varies right along with it. Skip wave or skip propagation is responsible for, sky wave or skip propagation is responsible for most over the horizon propagation on HF and low VHF. Low VHF being considered 10 meters and 6 meters. And again, these are two technician bands. You've got full privilege on 6 meters. You've got a little bit of privilege on 10 meters. Skip is very rare on 144, that's 2 meters and higher UHF bands. Each ground to sky to ground trip is called a hop. These signals can take many paths through the atmosphere because, again, as I said, an antenna is transmitting not just one or two lines like we see in these illustrations, but it's a continuous path of signals going out. Randomly combining at the receiving antenna, signals can partially cancel, creating irregular fading as the ionosphere changes. And this is where I had mentioned earlier, that is not a smooth layer edges. It varies from second to second. It'll vary because right now the sun is transmitting something very strong, but suddenly there's a flare. And all of a sudden now as the effects of that flare hit the earth, things begin to change. So this is a very uneven environment up there in the ionosphere, and that causes these radio signals to diffract and go off into different directions. The resulting echo and flutter distort speech and CW, Morse code. Fading causes data errors for digital signals. And again, a receiver can't quite copy that digital signal so well, it's going to miss some characters. And we saw that earlier on FM, where the diffraction will cause, and multipath propagation causes errors in the received signals. So again, more of the same. We're looking at multipath here up at the top. Signals are getting scattered because of the trees and the vegetation. It's diffracting off of a building. It's reflecting off of this building. Right here, it's multipath reception. So a little bit of fluttering, a little bit of your noise, your voice is a little buzzy. Things like that are going on. Much more pronounced, or if you bring this down to HF, just because in the ionosphere, the reflecting, the refracting, some diffraction going on in there, the receiving station is getting different signals. Even here, it's in the skip zone. It's underneath, but it's receiving reflected, diffracted signaling, reflecting back off over here. It backscatters and comes back down into the skip zone. So even though you're in the skip zone, sometimes you can actually get a radio signal. And again, that goes back to your, see, you asked such a good question. That was really good. Okay, now some special cases, sporadic E and aurora. Highly ionized patches of the E layer, right below the F layer, can reflect HF and VHF signals. And this is best on 10 meters, 6 meters, and 2 meters. You will hear it. And how will you hear it, especially in the summer and the midwinter, early summer, midwinter? And we'll talk about this in just a second. The aurora, thin sheets of ionized particles reflect VHF signals. And of course, we hear that mostly in the wintertime when the North Pole, which is relevant to us, is away from the sun. You can see these auroras much easier, much better. They're a little bit stronger, and you will know it on an HF radio when you hear those kind of signals. That voice just suddenly becomes very buzzy, and it may not happen for very long because these aurora borealis don't last forever. Sometimes they're a few seconds, sometimes they can last for 5 or 6 minutes or longer. But you will hear it because radio waves reflecting off of the aurora borealis sound much, much different. Meteor scatter. All right, this kind of goes back to what I was talking about with the airplanes, but here we're talking about meteor scatters. Thousands of meteors are coming through the Earth's surface all the time. We don't realize it, especially during the daytime. We don't see it. At nighttime, we don't see the small particles, but every now and then there's a chunk big enough. Hey, there goes a shooting star. And during meteor shower activity, hopefully you can see a lot of them. Meteors leave trails of highly ionized gas that last for several seconds, whether it's a little speck of dust or whether it's one of those bigger chunks. These trails can reflect radio waves, and it's called meteor scatter. And because it happens, mostly best band is at 6 meters, what we also refer to as the magic band. 6 meters, you've got total privileges as technicians on 6 meters. You can be experimenting with meteor scatter. It also takes place mostly in the E layer. Meteor scatter and sporadic E supports contacts up to 1,500 miles. So you can get practically, halfway across the United States on meteor scatter. Not sure what my next slide is, but I will say on 2 meters, even if you're talking to a repeater, as an example, I'm going to use the 7.6 machine in Williamsburg. There are mornings, usually in the springtime, when all of a sudden there's other traffic on our repeater. We are hearing Anne Arundel County way the hell up in Maryland, and sometimes we're picking up Charlottesville. They come in, I don't know if they're closer or just in a different direction. And then there's another one down in North Carolina that come in, they're transmitting on 7.6 as well. Their repeaters have the same pair. But normally we're far enough apart, the ground wave doesn't get that far, so we don't hear them, and it's UHF, or VHF rather. So we don't have to worry about a lot of things. But every now and then, sporadically, sometimes what's called tropospheric ducting, that comes up here in a minute, takes place. And now we're hearing all of them. They're hearing us. Doesn't happen very often, but it can happen particularly on 2 meters.
I've talked on my mobile, sitting in the driveway all the way to New York, just on, 25 watts.
Yeah, it's a very special thing when it happens. Everybody, run for your radio, get on there and make some contacts that you won't be able to make for the rest of the year. All right, meteor scatter. So there's the meteor trail. You're transmitting up into it. It reflects off of the meteor trail. Comes down way the hell over here. Oh, I'm sorry, way the heck over there. Tropospheric ducting. All right, now this also happens usually in the springtime, early summer. It happens when cold fronts are moving in, and we get those storms, April showers, or April showers, right?
Bring the
April,
flowers.
something brings the flowers.
May.
May, right? So April is the time that this all happens. A cool, dry air comes in over the top of warmer air on the bottom, and there's a layer in between the front, the two fronts, as it moves in. And so the radio wave, as it transmits out, the ground wave will go about this, a normal range, so everybody in here is picking it up. But at the same time, that layer ducks the radio signal far, far away, so it can come out way back up here in New York, for example. Tropospheric ducting is what that's called. VHF frequencies and higher. Weather temperature inversions create these layers, and you can get almost 300 miles off of, tropospheric ducting. So how do you tell? Is it tropospheric ducting or is it, sporadic heat? It might depend on how far away that other station is. If you're less than 300 miles, it's probably tropospheric ducting. If it's up there upwards of 1,500 miles, then you're talking sporadic heat. Sunspot cycles. Anybody know what sunspot cycle we're in right now? Or where we're at? We're on the downward slope of cycle 25. Sunspot cycles. The level of ionization depends on the intensity of radiation coming from the sun. Some of that is just the sun doing what the sun does. Sometimes it's the sun, it produces a solar flare, and that helps disrupt what's going on here in our ionosphere. Sometimes the sun barfs up stuff and it spits it at us. So all this projectile vomiting from the sun comes at us as a coronal mass ejection, and that also affects our ionosphere. We'll get into that stuff in the general class. But for a technician here, just knowing that radiation from the sun varies in many different ways, but in this class, what we're going to be concentrating on are sunspots, the number of sunspots on the sun and how active they are. High number of sunspots results in high levels of ionization radiation, and that's always a good thing. We like that as amateur radio operators. If the sun's going to barf on us, nobody likes to barf on us. So even amateur radio operators, we don't like CME ejections. Sunspot activity follows an 11-year cycle. Cycles up and down. And a couple of years ago, and a couple of very short years ago, we had long stretches of time where we didn't have any sunspots at all. And for HF operators, that was a very dull period of time. So we're in cycle 25. Cycle 25 started back here in about 2019. We were at a low. This is nothing was going on sunspot-wise. But as we progressed further and further, we reached a solar maximum over here. This is a prediction. Unfortunately, I didn't have time to get the most recent one because we definitely have now figures for this upward slope. But this turns out to be a pretty good projection. It was around July of last year we reached a peak. And so HF, including 10 meters, everybody's having a heyday. Because lots of sunspot activity, a lot of heavy sunspot activity. Now we're somewhere over here on the downward slope. So you guys are getting into amateur radio at a good time, especially if you intend to go up to general. You want to take advantage of what's left of our downward slope, because by the time we get to 2029, 2031, we're at the valley, and we're still going to have HF communication. But it's not going to be as good as it's been when you're at these peaks. So once you're down here, you're going to have to wait 5 to 6 years to get up there to the next peak. Important thing to know right now is that you're in sunspot cycle 25. Next one. Band conditions. Now I mentioned maximum usable frequency, lowest usable frequency, the muff and the luff. At the maximum usable frequency, we've been talking about incident angles, but there is also what affects this is the frequency. So as you change bands, this is why there are many different bands, particularly in the HF area. Sorry about that, Cynthia. Particularly in the HF bands, 40 meters. You might be working 40 meters and, oh, it's dead. The band closed for some reason. Don't know why. Maybe it's sunspot activity or lack thereof. But 40 meters just isn't working very well. But if you switch to 20 meters, a different frequency, all of a sudden now maybe you have gone from the lowest usable frequency, you've come across above that, but you haven't quite hit the maximum usable frequency. 20 meters is often in the sweet spot there, and that will work. So what frequency you're on also depends on whether your radio waves will bounce or go off into space. And this is one, I think this is kind of patronizing, but understanding propagation is fun. Yes, it is. It's a lot of fun. All right, a couple practice questions. Which region of the atmospheres refracts or bends HF and VHF radio waves, rather? There's only one answer, of course. Thank you. That means I got at least one person's awake. Thank you. Why are simplex UHF signals rarely heard beyond the horizon, the radio horizon? Are they too weak to go very far? And we're talking UHF and we're talking simplex. So we're not talking, there's no radio repeater involved here. They're too weak to go very far. FCC regulations prohibit them from going more than 50 miles. Does that strike anybody? Do you think a radio wave gives a hoot? Boy, that was a close call there. Gives a hoot to what the FCC says? UHF signals are usually not propagated by the ionosphere, or UHF signals are absorbed by the ionospheric D layer, which the slides never got into the D layer, so we can cross that off too. So usually it's not propagated by the ionosphere, they'll just go off into space. What type of propagation is responsible for allowing over the horizon VHF, UHF communications to ranges of approximately 300 miles on a regular basis? And here's my satellite. Yeah, this is not my favorite answer because they repeat it so often. This is dumb. Okay, F2 refraction, D region refraction, tropospheric ducting, and again, we know this is a dumb answer because D layer does nothing but absorb. So it's either F2 region refraction, and again, the slides didn't get into it. I don't know if your books did or not, but F2 is during the day, as well as F1. At nighttime, F2 and F1 combine together into a single F. So we're talking about daytime region refraction, and I don't think that's it here. It says a regular basis, so that leaves us with tropospheric ducting. What's characteristic of HF communication compared with communication on VHF and higher frequencies? a characteristic of HF. So we're in the lower bands. HF antennas are generally smaller. We haven't talked about antennas yet. But I can tell you they're not generally smaller. HF antennas are huge because the bandwidths are, the band spread's so long. HF accommodates wider band width signals. We haven't even talked about that. So these two are dumb answers. Long distance ionospheric propagation is far more common on HF, where there is less atmospheric interference on HF. Okay, well, again, I can tell you with D, if you listen to AM radio at night, AM is down there in the HF bands just below it. A lot of static sometimes. That's why we all love FM, because it's up there in the VHF area. So that leaves us with C. Long distance ionospheric propagation is far more common on HF than it is on UHF, or UHF, VHF, and higher. What's characteristic of VHF signals received via aural backscatter? Okay, that was that one signal came over on the other side of the Earth, but it bounced against the Earth and reflected some signals back into the skip zone. That was backscatter. I don't think it said that on the diagram, but I remember telling you that was backscatter. So characteristics, aural backscatter. They're often received from 10,000 miles or more. They are distorted and signal strength varies considerably. I kind of like that one. They occur only during wintertime night hours. I don't think so. Generally strongest when your antenna is in. No, I don't think that's it either. So B is our right answer. Any questions about this one? No? Good. Which of the following types of propagation is most commonly associated with occasional strong signals 10, 6, and 2 meters from beyond the radial horizon? Backscatter, sporadic D-layer absorption, gray line propagation. Most common would probably be, it's not so much backscatter, that's more down in the HF stuff. D-layer absorption, nothing to do with UHF, although it can occur D-layer absorption here in 10 meters. Gray line propagation, we haven't even discussed that. That'll be in technical or general. So sporadic E is what we're talking about. What band's best suited for communicating via Meteor Scouter? Anybody remember that one? Sure.
6.
6, the magic band. The magic band, 6 meters. What is generally the best time for long distance 10-meter band propagation via the F layer? F layer, from dawn to shortly after sunset, especially periods of high sunspot activity. I like that one. High sunspot activities for, we're here at the top of the HF frequencies up in the 10-meter band. This one also has high sunspot. So from shortly after sunset to dawn. So this is, B is nighttime, A is daytime. From dawn to shortly after sunset, low sunspot. Okay, these are the two dumb answers. Low sunspot activity means the little is happening, but they're talking about the best time. And so believe it or not, and again, this was in an earlier slide, it's A, during shortly after, from dawn to shortly after sunset is the best time for doing this. What causes tropospheric ducting? Discharges of lightning during electrical storm? No. Sunspots, solar flares? No, not so much. This affects ionosphere. We're talking tropospheric ducting affects mostly 2 meters and up. Updrafts, doesn't matter if it's a hurricane or a tornado, so we're talking temperature inversions.
Gary, just a question.
Yeah.
Could it happen in hurricanes? Is it,
Yes, it can, but not due to updrafts.
oh,
Again, temperature inversions is usually because one air mass is coming over the top of another. Hurricanes swirl everything up. Tornadoes don't do that up above, that does it swirling down at the ground. Which of the following bands may provide long-distance communications via the ionosphere's F region during the peak of the sunspot cycle? So we're talking during the peak, this is a good thing. We're talking F region. This is a good thing because we know it's up in the F region where most of the refracting takes place. So which of the following bands may provide long-distance communication? 6 and 10, 23 meters, 70 centimeters, and 125 meters, or all of these choices are correct. Who said it?
Okay.
Yes. Hey, why?
We don't talk centimeters, so that's B and C, and then all of them, that means, yeah, centimeters, so.
Yes, this is true. This is going to be really great for HF. Really great. Doesn't matter what band. HF bands. The only HF bands up here are 6 and 10 meters. And 6, again, the magic band. That's right on the edge of HF and VHF. But it is included in this. But this is 23 centimeters, that's 1.2 gigahertz. 70 centimeters are the popular 70 centimeter band, 440, 1.25 is 220. So D is, all these choices are correct, is not true. All right, we're going to get into antenna radio wave basics coming up. We're at 10:30. This ain't going to make it. Anyway, take a quick break and come on back.